Pop science outlets often frame quantum computing through a specific analogy. Where a classical computer tests passwords one by one, a quantum machine checks every possibility simultaneously in a massive parallel sweep. Imagine a black box function that hides a single target value among n possibilities. If you can only find it by guessing and checking, a classical computer takes n over 2 attempts on average. But for a quantum computer, what is the best possible runtime for this search? If you pose this exact puzzle to attendees of the International Math Olympiad, the most common answer is that it happens instantly. When the same question is presented to elite computer science students at Stanford, they almost always fall into the same trap. This chart tracks the most common assumptions. People assume the runtime is an instant flat line of O of 1, or perhaps a slow rising O of log n. They guess these numbers because they are holding on to that idea of parallel processing. In reality, the absolute limit for this search is O of the square root of n. The runtime scales quadratically. Searching 1 trillion options takes 1 million steps. It is faster than a classical computer, but it is not instantaneous. Because the actual mathematics of the search contradicts the parallel processing myth, we have to discard that analogy entirely. To find the source of this square root speedup, we have to look at the underlying geometry. A quantum computer operates on a continuous state vector, an arrow in multidimensional space. Under the Born rule, squaring its alignment with an axis gives the probability of measuring it. To start, we position the vector at a perfect diagonal, evenly distributing probability across all answers. Now we apply the verification function to identify the solution. In a quantum setting, this operation isolates the target bit string and flips its sign. Next, we have a second operation. We take the state vector and reflect it completely around that initial balance position. Flipping a sign alone doesn't change the probabilities, but bouncing between these reflections lets us manipulate the invisible probability distribution before a measurement is forced. We compress our search into a 2-dimensional slice, wrong answers on the horizontal axis, the target on the vertical. Applying the verification function mirrors our mostly horizontal balance vector downwards. The balance flip then reflects it upwards, rotating it closer to the target axis. This is the core of Grover's algorithm. You repeat this sequence over and over. Flip the sign, then flip around the balance line. With every repetition, more probability mass transfers toward the correct answer. The math of this rotation determines the speedup. The vector's initial angle is roughly 1 over the square root of n. Rotating it 90 degrees requires multiplying by a factor of the square root of n steps. This specific geometric rotation through a high-dimensional space is the mathematical origin of the famous square root speedup. After the exact calculated number of rotations, the invisible state vector is pointing almost entirely in the vertical direction, loaded with the probability of the target bit string. It is only at this moment that you measure the system. Looking at the computer forces the probability distribution to collapse, cementing the correct answer into a readable physical reality. This speedup comes from a geometric shortcut. While a classical system is confined to moving between perpendicular coordinate axes, the quantum computer traces a continuous path along the arc of the state space. This mechanic creates a unique tension in scenarios where time is a critical resource, such as trying to solve a cryptographic puzzle while an adversary breaks down the door. If the computation is interrupted early, the state vector might only be 30% rotated. Measuring at that moment forces a collapse, likely resulting in a random bit string rather than the solution. The geometry must be allowed to complete its full arc. The success of the search depends on the uninterrupted orchestration of these rotations. The target value only becomes visible once the geometry has concentrated the probability mass into a single direction.